Look at this monster. This is the giant UltraFan aircraft engine with 87,000 horsepower from Rolls-Royce. Its diameter is over 3.5 meters. The UltraFan will run exclusively on eco-friendly aviation fuel, sustainable aviation fuel, sustainable aviation fuel. Testing of the UltraFan is set to begin at the start of 2023. And, as they say, a big engine needs a big test stand. In fact, the largest in the world. The site with Test Bed 80 was launched 2 years ago and was specifically designed for the development of the UltraFan. And just recently, they brought in the so-called demonstrator, which was created specifically for this giant. Most viewers of this video have likely flown on an airplane. But it's unlikely that each of you knows how the engine of this machine actually works. What's inside? A fan, a turbine, or maybe a couple thousand little gnomes pedaling special pedals? Let's figure it out. At the dawn of aviation, piston engines ruled the scene. Now, they've almost become a thing of the past. Although, how should I put it? Meat? This is the Celeira 500 LA prototype single-engine piston aircraft. The aircraft looks like an egg with wings and resembles a children's toy, but its capabilities are very serious. By using an unusual shape, the engineers reduced aerodynamic drag by 59%. Not bad for a toy. The Celeira's closest competitor is the Boeing business jet. Let's compare the technical specifications of the aircraft. The cruising speed of the Celeira is 740 km/h, and its range is 8,300 km. The cruising speed of the business jet is 842 km/h, and its range is 11,519 km. It seems pretty close, but for every 100 kilometers, the Boeing uses 258 liters of fuel, while the Celeira uses only 13. It turns out that this funny-looking plane is more economical than an SUV in city traffic, and if the pilot wants to save even more fuel, he can simply turn off the engine. With the engine off, the Celeira can glide for more than 200 kilometers. There are other examples of modern engineering that are connected to the seemingly outdated propeller. This is the world's first 11-blade propeller. It successfully completed its first test flight, as reported in a press release by its developer, MT Propeller. This is another achievement for the company, which previously produced 5, 7, and 9-blade propellers. The group of developers recorded a 15% increase in static thrust of the new propeller compared to the company's 5-blade propellers. The aircraft's propeller system, combined with a low revolutions per minute power source, can open up new possibilities for performance, efficiency, and low noise levels. After all, even an electric motor can be a low revolutions per minute power source. However, despite all these exceptions to the rule, it's not piston aircraft engines with propellers that dominate today, but two other types. The most popular engine installed on modern commercial airplanes is the Turbofan. Its advantage is that it's quite compact. The airflow in it moves through two circuits. In the inner circuit, the air is compressed by a compressor, ignited, spins the turbine, and is expelled through the nozzle, creating thrust. The second circuit starts with a large fan that we see from the outside. The fan drives and moves air through the circuit, creating additional thrust and increasing the engine's efficiency. Let's explain this system further with the PD-14, a fifth-generation engine, as an example. Don't mix up fifth-generation engines with fifth-generation fighter jets. Engines like these from the World War II era could heat up to 900 degrees, and by the fifth generation, this threshold has actually doubled. At the same time, the ability to operate in this mode for a long period also increased. At the front is the compressor, whose job is to compress the air passing through it. The air is pushed forward by stages, rotating disc structures of complex shape with blades around the circumference. Essentially, these are fans. There are as many as 11 of them here, 3 low pressure and 8 high pressure. Moreover, as the air moves through the engine, the number of blades increases, while the volume through which the air passes decreases. So, the air turns from a cool breeze into a hot gas, with its pressure increasing by 40 times. Next after the compressor comes the culprit of the fiery show, a low-emission combustion chamber, where fuel is injected and ignited, heating it up to almost 2,000 degrees. The chamber itself is a work of art. The design, with a very intricate flow configuration and including 48 injectors, is so complex to manufacture that its parts are 3D printed from metal. And this is not just a nod to industrial fashion. Otherwise, creating such a compact and reliable mechanism is impossible. In the turbine, the process is essentially the opposite of the compressor. Now, the hot, compressed air rushes through the mechanism, first hitting 2 high-pressure stages and then 6 low-pressure stages. The gas rotates the stages, transferring energy through the turbine to the shaft, which drives the fan and compressor stages that compress and push the gas here. That's the cycle of energy in the engine. The hot gas that has passed through the turbine bursts out with a roar through the nozzle, creating jet thrust. The main challenge for engineers in the hot section is the components that come into direct contact with the working area, primarily the blades. They must be able to withstand enormous loads without melting or breaking apart. There are several solutions to this problem. First, specially designed heat-resistant alloys. Second, there are special channels inside these housings through which air flows, cooling them from the inside. As a final touch, there are special ceramic coatings that take the first impact of the heat. These solutions, in various combinations, allow the blades to function properly. The outer contour is simpler. No combustion chamber, turbine, or more than one fan. But what a fan it is! It's made up of hollow titanium blades. Unlike the regular metal blades you can see on most aircraft engines, these new blades are lighter, larger, have a complex aerodynamic shape, and don't require additional reinforcing elements. Yes, they're still a bit heavier than composite ones, but again, it's a matter of balance. Composite blades are quite complex and expensive to manufacture, and the weight advantage becomes crucial as their size increases. Composite fans are not used on large engines. You end up with the same result for a higher price. On the other hand, on large engines, composite fans are actually the only viable option. Metal would be too heavy here. Now we're about to see a maze of units, cables, pipes, pumps, and sensors lining the outer contour of the engine. People rarely discuss them, since it's difficult to understand what they are. But without all of this, any aircraft engine is just an art object. The engine's component base is almost entirely Russian. There are only 4 countries in the world capable of creating modern turbofan engines through a full production cycle: the United States of America, the United Kingdom, France, and Russia. Each of them strictly protects their research results and know-how in engine building. For example, France produces the hot sections of the CM-146 engines only on its own territory. These units take years to design. A modern aircraft engine takes 1.5 to 2 times longer to develop than the aircraft. For example, the PD-14 began development in 2008. The designers implemented 16 key technologies which cannot be mastered without creating your own production facilities. The second type of engine is the turbojet. Such an engine is quite bulky and is usually used on military aircraft of various classes. For installation, either a section of the carrier aircraft's fuselage is used or special recesses along its sides. The turbojet engine has high power and, as a result, helps the aircraft reach high speeds, up to and including supersonic. In a turbojet engine, air is drawn into the compressor, which is powered by an external cold turbine, and after compression, it is supplied to the hot turbine. This engine is not economical at all, which is why it is very rarely used in civil aviation. However, this has happened in history as well. The most obvious examples of turbojet engines being used on civil aircraft are the Supersonic Concorde and Tu-144. Let's take a closer look at them. The development of the supersonic aircraft Tu-144 was first announced in 1962. It was positioned as a direct response to the foreign Concorde, which was supposed to be the first passenger aircraft to break the sound barrier. However, the first flight of the aircraft from the Tupolev Design Bureau took place on December 31, 1968, 2 months earlier than the Concorde's flight. The Tu-144 and Concorde supersonic aircraft are often seen as twins. Some people are convinced that the aircraft have many similarities because one side stole the blueprints from the other. But in reality, engineers from the Soviet Union, the United Kingdom, and France often met and discussed their ideas. There are similarities and very significant ones, but at the same time, the aircraft also have major differences. The main differences are the Tupolev 144 has nose canards, while the Concorde does not. The Tupolev 144 used large solid plates, while the Concorde used many small riveted parts. The Tupolev 144 was equipped with the NK-144 jet engine, while the Concorde had the Olympus 593 engine. However, the fate of these two aircraft is very similar. Supersonic passenger planes were retired from service due to a series of accidents. For the first time, the Soviet Tu-144 crashed in 1973 during the air show in Le Bourget. 6 crew members and 8 people on the ground were killed. The second time, the aircraft crashed in 1978 during a test flight, resulting in the deaths of 2 flight engineers. The third emergency occurred in 1980, when one of the engines of the prototype was destroyed during testing. Fortunately, the crew took control of the situation, landed the aircraft, and survived. In 1981, the aircraft was already preparing to begin commercial flights, but a fire broke out on board, and the crew had to evacuate the aircraft through the emergency exits. After all that, interest in the aircraft disappeared. However, later it was sometimes used for sleeping. Urgent cargo and mail flights operated between Moscow and Khabarovsk. The last flight was made in 1999. The Concorde aircraft got into trouble much less often than its Soviet counterpart. But the disaster that happened in Paris in 2000 turned out to be the most tragic. During takeoff from Paris to New York, the left landing gear of the Concorde ran over a piece of another plane's fuselage, which caused a fire. The disaster claimed the lives of not only all 100 passengers and 9 crew members on the plane, but also 4 people who were in the hotel. After this terrible event, they tried to continue using the aircraft, but after several more malfunctions, the project was shut down. But even if we don't talk about supersonic planes, can't we just make a regular plane fly faster? Yes, we can, and they are capable of reaching those same 800 to 900 kilometers per hour, which often becomes the cruising speed of regular airliners. But there's just no point in doing that. The costs will increase significantly, while the travel time will be reduced by just about 10 minutes, especially if the flight isn't a long one. There's another question that might interest a typical airline passenger. Why don't airplane engines stall during rain? And how dangerous is it to fly in a downpour? Most car owners know that water should never get into the engine under any circumstances. Moisture in internal combustion engines can cause severe damage, including broken parts and engine rupture. But airliners fly using engines that convert the thermal energy of fuel. Therefore, their engines should not have water, yet aircraft engines lack moisture protection systems. Planes don't even have bird screens installed in front of the engines. So how do airliners fly in the rain? Why doesn't water harm their engines? An airliner can fly in heavy rain. At this time, every cubic meter of air contains 10 cubic centimeters of water. The airplane engines take in huge amounts of air, so on average, about 1 liter of water enters the engines every second. In just a few minutes, a significant amount of liquid should accumulate. But why doesn't it stall the engine or cause it to fail? First of all, the airflow in airplane engines is distributed at a ratio of 1 to 10. Most of it doesn't go into the engine itself, but into the outer bypass. 90% of the air passes through it, increasing thrust. Some of it also serves as cooling. The air is captured by something like a fan. It acts as a centrifuge. Under its influence, the heavier water particles end up near the walls of the outer bypass, while the lighter air stays in the center. Next, the air masses enter the compressor. As a result of compression, the gases are heated up to 260 degrees. Accordingly, the water evaporates even before it actually enters the engine. The second reason water doesn't harm airplane engines is their size. That 1 liter of liquid per second that could potentially get into the engine is negligible on its scale. Modern airliners are tested for safety, and it is ensured even with 75 liters of water per second, which is impossible in the sky even during the heaviest downpour. A much greater threat to an airliner can be hail, because solid particles will hit the fuselage and engine at bullet speed and will behave very differently from water. But this atmospheric phenomenon is much rarer and more predictable, and almost always, airliners have enough time to avoid the hail zone. And here's another interesting question, by the way. Why did they stop making such beauty? Why don't they install engines inside the airplane wings anymore? The first commercial airliner in history to be equipped with 4 engines mounted inside the wings was the British de Havilland de Havilland 106 Comet, which made its first flight back in 1949. And already in 1955, the Soviet Tu-104 with engines built into the wings took to the air, and a similar design was also used in the Tu-124. So why was the decision ultimately made to abandon this component? At first glance, it has a clear advantage. The first and probably main advantage of engines in the wings is an aerodynamically clean wing, which in turn allows for significantly greater lift. And for the first jet airliners, this was indeed a critically important factor. After all, if we look at the same Comet, it was originally equipped with engine installations. Rolls-Royce Avon, with a thrust of 32.7 kN, which is incredibly low. And if we look at the Rolls-Royce Trent 7000 engines with a thrust of 324 kN, the difference is obvious. Another advantage of built-in engines was the lower yawing moment in case of engine failure. Yes, modern engines rarely break down these days. Statistics show 1 failure per 100,000 flight hours, but back then, 1 failure per 2,500 flight hours was considered a good indicator. So back then, engines failed almost 40 times more often. The third advantage is a lower tendency to ingest debris compared to engines mounted under the aircraft wing. But this configuration also had its drawbacks. For example, if there was a fuel leak resulting in an engine fire, there was a high probability that the wing itself, as well as the neighboring engine, would be damaged. If we look specifically at the Cometa, but an engine suspended under the wing is quite well isolated and, in fact, can even burn out completely without causing significant harm to the airliner as a whole. Among other things, an engine mounted higher is simply harder to service because of its higher position. Another significant drawback is the inability to upgrade the engines without serious structural changes, because when replacing a built-in engine, it was inevitably necessary to adjust the wing geometry. And that's far from a cheap undertaking. In this regard, the Boeing 737 is a true example of rational cost saving. This airliner has been produced for 54 years now, and during this time has undergone 4 major redesigns with engine changes. At the same time, the fuselage itself has changed very little. In addition, the advantages of placing the engine under the wing include these factors: more space in the wings for fuel. At the same time, if the fuel supply system fails, the fuel will flow to the engines by gravity. Besides that, the suspended engines also help balance the wings themselves, damping unwanted vibrations, which also allowed for lower strength requirements, and, therefore, made them lighter. These advantages determined the appearance of modern airliners, while engines inside the wing were relevant only at the very dawn of civil aviation. In today's reality, flights on airplanes with such a configuration would be too expensive and impractical. In this episode, we covered only a part of the questions related to the fascinating topic of aviation, and we will continue to do so in future episodes. Set up notifications so you don't miss them. Thank you for watching, and see you on our channel.